Part 1. The Milky Way, our home in the immensity. You lift your gaze toward the heavens on a clear night. Thousands of stars flicker before you, a luminous river cutting through the darkness. That is the Milky Way, the galaxy we inhabit. It holds hundreds of billions of suns, planetary systems, and unanswered mysteries, so immense that even numbers fail to capture its scale. And yet, when placed against the backdrop of the full cosmos, our galaxy becomes nothing but a faint glimmer, a tiny particle drifting in a boundless sea. It reminds us that what seems immeasurable may only be the beginning of something far more colossal. Good evening, and welcome to our channel. Tonight we begin an unhurried journey, a calm passage through constellations and galactic structures, crafted to accompany you as your eyelids grow heavy and tranquility settles around you. Seen with the naked eye, the Milky Way appears to be no more than a soft, glowing haze stretched across the sky. But what you actually witness is the merged radiance of billions of distant suns, each so far away that their combined light forms a continuous band. It's similar to looking at a brightly lit stadium from an enormous distance. From so far off, you wouldn't distinguish each individual lamp, only a wide wash of brightness. The same effect occurs with the Milky Way. Our eyes cannot pick out every star within it, yet together they create the brilliant torrent countless civilizations have admired long before us. The Milky Way is not an ordinary cloud of light. It has a very specific structure. Researchers of the cosmos have determined that it is a barred spiral galaxy. Picture a swirl formed when a spoon stirs milk into a cup of coffee. Curved arms emerge and rotate around a central point. That's our galaxy. At its core lies a radiant bar-like formation of stars, a luminous axis cutting across the center, from which the spiral arms unfurl. Within those arms gather young stars, clouds of gas, and drifting cosmic dust. The scale of this structure is so astonishing that it defies easy comprehension. Scientists estimate the Milky Way spans roughly 100,000 light-years from end to end. If a beacon were lit at one extremity, its light would require 100 millennia to reach the opposite side, moving at the fastest speed nature allows, the speed of light, nearly 300,000 kilometers per second. Now shift into more familiar terms. Imagine boarding a commercial airliner cruising at around 900 kilometers per hour. If you attempted to cross the Milky Way at that pace, the trip would take more than 100 billion years. To put this in perspective, the universe itself is only about 13.8 billion years old. This means that even if the journey had begun at the instant the universe was born, we would still be mid-flight, far from completing half the distance. It reveals, with undeniable clarity, just how tiny our swiftest machines are when measured against cosmic dimensions. The galaxy's immensity extends beyond mere size. It is also abundant in content. Current estimates suggest the Milky Way contains between 100 and 400 billion stars. Try to visualize a number like that. If each star were a grain of sand, you would have to fill an entire beach. And even then, our galaxy would represent only one such beach, because the cosmos is filled with galaxies just as rich or even greater in number. Among those billions of stars, one stands out to us: the Sun. The Sun doesn't sit at the center and holds no privileged location. It lies in a relatively quiet region, situated in one of the spiral arms known as the Orion Arm. You could say we live in the outskirts of the galaxy, a peaceful celestial suburb far from the intense commotion at the galactic core. And perhaps that distance was a blessing. At the heart of the Milky Way rests a supermassive black hole called Sagittarius A star, a domain so violent that life as we know it would have almost no chance of arising there. The idea that the Milky Way is our cosmic home is not merely poetic, it is literal. Here the stars formed that created the elements from which we are made. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in ancient stars born and extinguished within this very galaxy. In a sense, the Milky Way is not simply the place we reside. It is a cosmic mother that supplied the materials of our existence. Throughout history, civilizations have regarded that bright band across the sky as something exceptional. To the ancient Greeks, it was the galaxias kyklos, the Milky Circle, from which our word galaxy descends. In South America, various indigenous cultures viewed it as a celestial river guiding the souls of the departed. The Maya called it Xibalba Bay, the road to the underworld. In every tradition, the Milky Way was more than an astronomical sight. It was a symbol, a bridge connecting the heavens with human life on Earth. Today we understand that what they saw was the interior view of our own galaxy. It's like standing in the center of a forest and turning in any direction. Trees stretch around you, and overhead the sky is threaded with branches. In the same way, when we look toward the Milky Way, we are gazing through the dense stellar branches encircling us. The Milky Way also has small galactic companions, dwarf galaxies orbiting it like satellites. The large and small Magellanic Clouds are the most prominent among them. They are like smaller partners following a greater world, contributing stars and matter to the long cosmic choreography unfolding over millions of years. And despite the overwhelming scale, the Milky Way still feels like home. It is the place we belong, even though we will never traverse it entirely. A home doesn't need to be walked from corner to corner to be truly ours. Just as a nation can feel like home even if you never visit every city, the galaxy can be our home, even if we never witness all its distant reaches. This sense of belonging to something so vast can be comforting and unsettling at once. Comforting because it shows we are part of a system far larger than ourselves. Unsettling because it reveals that even what we consider immense is only a fraction of something far beyond it. Here, imagination becomes essential. Picture the Milky Way, not from Earth, nor through a telescope, but from a distant vantage point in space, far enough to see the entire structure at once. You would behold a magnificent spiral, its arms laden with shining stars that gleam like tiny points of light, rotating slowly around a brilliant core. A quiet, yet overwhelming spectacle. And somewhere in one of those arms, almost invisible from afar, lies our sun. And circling that sun is a small blue world where, at this very moment, you are breathing. Thinking about this naturally brings a mix of wonder and humility. Humility because we recognize we hold no central place in the galaxy. Wonder because, despite our smallness, we are capable of imagining all this, of grasping scales that far transcend everyday life. The Milky Way is our cosmic neighborhood. It may appear infinite, yet it is only a slice of the universe. It is like the street where you grew up, enormous through the eyes of a child, but merely one section of a city. And that city just a fragment of the world. Little by little we realize our galaxy, despite its splendor, is not the entirety of existence, but only the opening chapter of a far larger map. And as in any neighborhood, we are not alone. Around us lie stars, planetary systems, and galactic neighbors, sharing this region of the cosmos with us. Part 2. Our stellar neighborhood. The Sun, our star, seems singular from our earthbound viewpoint. It is the source of light and warmth that makes life possible on our planet. Yet on a galactic scale, The Sun is nothing more than an ordinary star among hundreds of billions. It is like a single house along an immense avenue surrounded by countless others, each with its own history. If the Sun were our home, who would our nearest neighbors be? The closest star to us is Proxima Centauri, positioned about 4.2 light-years away. This means the light leaving Proxima Centauri takes just over 4 years to reach us. In cosmic terms, that is relatively close, which is why we call it our nearest neighbor. But it is worth examining what that distance truly implies. A light year is the distance light travels in a year, moving at nearly 300,000 kilometers per second. Calculate it, and you get roughly 9.5 trillion kilometers. Multiply that by 4.2, and you obtain the distance to Proxima Centauri, around 40 trillion kilometers. It is a figure so huge that it challenges comprehension. Let's place it into something more graspable. The fastest spacecraft humanity has ever built is the Parker Solar Probe, reaching speeds of about 650,000 kilometers per hour when sweeping near the Sun. By our standards, that is astonishingly fast. Yet even at that extraordinary pace, the probe would need more than 6,500 years to reach Proxima Centauri. If we had launched it during the era of the earliest Egyptian civilizations, it would be arriving only now. And Proxima Centauri is our closest star. The others lie much farther away. Sirius, the brightest star in the night sky, sits 8.6 light-years from us. Vega is 25 light-years distant. Betelgeuse, the iconic red supergiant in Orion, rests roughly 550 light-years away. Each of these stars is a sun with its own existence and possibly its own family of planets circling around it. Within our immediate stellar neighborhood, dozens of stars lie within a 20 light-year radius. Some are smaller and fainter than the Sun, red dwarfs that glow with minimal brightness yet may endure for trillions of years. Others are giants, massive stars burning their fuel rapidly and destined to end their lives in spectacular supernova explosions. Each follows its own path and story through the galaxy. The Orion Arm, where the Sun resides, is something like a galactic suburb. It is not one of the Milky Way's primary spiral arms, but rather a secondary arm or spur. Here the density of stars is moderate, not as crowded as the main arms, yet not as sparse as the outer reaches. It is a relatively calm region, free from strong gravitational disturbances and without frequent nearby supernova detonations. This calmness may have been crucial for the emergence of life on Earth. Think of it this way. Had the Sun formed closer to the galactic center, cosmic radiation would have been far more intense. Nearby supernova blasts might have showered Earth with lethal cosmic rays, wiping out early life. Gravitational encounters with passing stars could have destabilized planetary orbits, ejecting worlds into interstellar darkness or hurling them into the Sun. But here, in our peaceful corner, life had time and stability to evolve across billions of years. Our stellar neighborhood is not static. The stars are not fixed like points on a painted mural. Instead, all of them move, orbiting the galactic center along different trajectories and at differing speeds. The Sun completes one orbit around the Milky Way's center roughly every 225 million years, a galactic year. Since dinosaurs roamed Earth, the Sun has completed slightly more than a quarter of one such orbit. Since the solar system formed 4.6 billion years ago, the Sun has circled the galaxy around 20 times. As it travels, the Sun also oscillates vertically relative to the galactic plane, rising and dipping like a carousel horse. Every roughly 33 million years, it crosses the galactic plane. Some researchers have speculated that these crossings might correlate with mass extinctions on Earth, though the idea remains under debate. During this long orbital voyage, the Sun and its retinue of planets pass through various stellar neighborhoods. Millions of years ago, other stars were our closest companions. Millions of years in the future, different stars will drift into that role. It is like staying in the same house while the entire neighborhood rearranges itself around you. Some of the stars in our current vicinity may host Earth-like planets. Advances in exoplanet detection have revealed thousands of worlds orbiting distant suns. A portion lie within the so-called habitable zone, where temperatures allow liquid water to exist on a planet's surface. Proxima Centauri, our closest neighbor, has at least one confirmed planet, Proxima Centauri b, located within that habitable region. Could life exist there? We don't know. Proxima Centauri is a red dwarf, cooler and smaller than the Sun, but vastly more active in terms of stellar flares. Those eruptions may have stripped the planet's atmosphere or prevented complex life from taking root. Yet life can be remarkably resilient, so it is also conceivable that it has found a way to endure despite hostile conditions. We currently lack the instruments to confirm either possibility, though each technological leap inches us closer to answering a timeless question: are we alone? Not all objects in our neighborhood are stars. There are brown dwarfs, bodies too large to be planets, but too small to ignite nuclear fusion in their cores. There are rogue planets, worlds expelled from their home systems, now wandering alone through interstellar space. There are stellar remnants, white dwarfs, neutron stars, and possibly even stellar mass black holes, the compact remains of stars that died long ago. And there is the interstellar medium, clouds of gas and dust adrift between the stars. These clouds are stellar nurseries. When a cloud becomes dense and cold enough, it collapses under its own gravity, fragmenting into smaller clumps. Each clump contracts and heats until, deep within its core, the temperature and pressure surge high enough for nuclear fusion to ignite. A new star is born. Around it, spinning in a disk of leftover material, planets may form. This is how our Sun emerged billions of years ago, and stars continue to form throughout our galaxy in the same way today. Our stellar neighborhood is thus a dynamic, diverse environment. It is not an empty void, but a cosmic ecosystem where stars are born, evolve, interact, and die. Where planets form and may harbor life. Where interstellar space teems with shifting matter and energy. And all of this takes place in a relatively small corner of the Milky Way, within our segment of the Orion Arm. When we look up at the night sky, most of the stars visible to the naked eye lie within just a few hundred light-years. They are our immediate cosmic neighbors. Beyond them are billions of others composing the rest of the galaxy, but they are too distant and faint to be seen without instruments. This stellar neighborhood is our starting point, the immediate context in which our solar system exists. And although the distances within it are immense by human standards, they are tiny compared to what comes next. Because beyond our neighborhood, beyond the Orion Arm, lies the rest of the Milky Way, and beyond the Milky Way the universe expands into structures even more grand. Part 3. Beyond our galaxy, the discovery of other worlds. For centuries, humanity believed the Milky Way was all that existed. In our understanding, the universe ended at the edges of our own galaxy. Beyond that boundary, we imagined only emptiness. This view began to shift in the 18th century, when astronomers noticed faint, diffuse patches in the sky that did not resemble individual stars. They called them nebulas, from the Latin nebula, meaning cloud. Some of these nebulas were indeed clouds of gas and dust within our own galaxy, sites where new stars were being born. But others appeared different, more structured, with spiral or elliptical shapes. Astronomers debated fiercely. Were these nebulas parts of the Milky Way, or were they something entirely separate? In 1920, astronomer Edwin Hubble transformed our understanding of the cosmos forever. Using the 100-inch Hooker telescope at Mount Wilson Observatory, the most powerful instrument of its era, Hubble studied the Andromeda Nebula. Within it, he identified a type of pulsating star known as a Cepheid variable. These stars possess a remarkable property. Their brightness varies in a predictable cycle, and there is a direct relationship between their pulsation period and their intrinsic luminosity. By measuring the time they took to brighten and dim, Hubble determined their true brightness. Comparing that to how faint they appeared from Earth allowed him to calculate their distance. The results were astonishing. The Andromeda Nebula lay roughly 900,000 light-years away, far beyond the boundaries of the Milky Way. Hubble had proven that Andromeda was not a cloud within our galaxy, but an entirely separate galaxy, a vast star system comparable to the Milky Way itself. Overnight, the universe expanded. We were no longer alone in the cosmos. Our galaxy was only one among many. This discovery was revolutionary. It echoed Copernicus shifting Earth out of the center of the solar system, and Galileo revealing moons orbiting Jupiter, proof that Earth was not unique. Now the Milky Way, too, was no longer singular. Other island universes, as Immanuel Kant had proposed a century earlier, floated throughout space. Andromeda, catalogued as Messier 31 or M31, is the nearest large galaxy to us. It lies about 2.5 million light-years away. When we observe Andromeda today, we see light that began its journey 2.5 million years ago, when our distant ancestors were just beginning to walk upright on the African savannas. That ancient light traveled across empty space all that time before reaching our eyes. Andromeda is a spiral galaxy like our own, though slightly larger. It contains around 1 trillion stars, more than twice as many as the Milky Way. From the northern hemisphere, on a very dark and clear night, you can spot it without a telescope as a faint, elongated blur. It is the most distant object visible to the naked eye, and when you look at it, you are gazing across both space and time. But Andromeda is not our only galactic companion. There are also the Magellanic Clouds, the large and small Magellanic Clouds, visible from the southern hemisphere. These dwarf galaxies orbit the Milky Way, far smaller than our own, but still containing millions of stars. The large Magellanic Cloud lies about 160,000 light-years away, while the small cloud is around 200,000 light-years distant. They circle our galaxy like enormous moons, bound to us by gravity. These clouds were named after the explorer Ferdinand Magellan, who recorded them during his 16th century circumnavigation. Indigenous peoples of the southern hemisphere had known them since long before his arrival. Australian Aboriginal cultures wove them into creation stories. Polynesian navigators used them as celestial markers during ocean voyages. The Magellanic Clouds hold special interest because they are close enough to study in detail. We can observe individual stars within them, measure their properties, and trace their evolution. They are cosmic laboratories, offering insight into how galaxies form and change. And slowly, under the gravitational pull of the Milky Way, they are being torn apart. Over billions of years, they will be fully absorbed, their stars becoming part of our own. The realization that other galaxies existed opened floodgates. If one galaxy lay beyond the Milky Way, how many more might there be? Hubble and others began systematic searches. They found galaxies in every direction, spirals like the Milky Way and Andromeda, elliptical galaxies with rounded shapes and no spiral arms, and irregular galaxies lacking clear structure. Each galaxy was an entire system. Each contained billions or even trillions of stars. Each star potentially hosted its own planets. the number of possible worlds in the universe multiplied immeasurably. If earlier we had wondered whether planets existed in our galaxy, now we had to consider planets in millions of galaxies. Hubble went further still. He not only demonstrated the existence of other galaxies, but uncovered a second profound truth: the universe is expanding. Examining the light of distant galaxies, he noticed that most exhibited a redshift in their spectra, meaning they were moving away from us. And the farther a galaxy was, the faster it receded. This provided the first observational evidence that the universe was not static, but dynamic. It was stretching outward. The implications were immense. If galaxies are moving apart now, then in the past they must have been closer together. Rewind time far enough, and every galaxy, every atom of matter and energy, occupies the same extremely dense, hot point. This insight led to the development of the Big Bang theory, the idea that the universe had a definite beginning, about 13.8 billion years ago. The discovery of other galaxies also revealed that the universe has large-scale structure. Galaxies do not lie randomly scattered. They cluster. They form neighborhoods, groups, clusters, and even superclusters. The Milky Way, Andromeda, and roughly 50 smaller galaxies form what we call the local group, our immediate galactic neighborhood, which we will explore soon. Before we delve into that, consider the significance of this discovery. Edwin Hubble, through diligence and scientific precision, expanded the human view of the cosmos in a way few before him had matched. Before his era, we imagined ourselves confined to a single island in darkness. After his work, we found ourselves in a vast archipelago of galaxies. Our perspective shifted at its very foundation. Discoveries of this magnitude remind us of the power of curiosity and exploration. They show that the universe always holds more layers than we expect. Every answer spawns new questions. Every boundary crossed reveals horizons farther still. And far from discouraging, this is exhilarating. It means there is always more to uncover, more to learn. When we look at Andromeda now, we do not merely see a smudge of light. We see a vast system of 1 trillion suns, each with its own story. We see worlds we may never know, but whose existence reminds us that we are part of something far larger. And we also glimpse our own future. For Andromeda is not simply drifting in space, it is slowly moving toward us. Part 4. The Local Group and the Destiny of Galaxies. The Milky Way and Andromeda do not drift alone in the cosmos. They belong to a larger structure known as the Local Group, a gathering of roughly 50 galaxies bound together by gravity. It is a cosmic neighborhood in which each galaxy is a house, and all share the same gravitational landscape. The Local Group spans about 10 million light-years. It seems enormous, because it is, but on a universal scale, it occupies only a small corner. Within this group, the Milky Way and Andromeda dominate. They are the largest and most massive members, and their gravity shapes the motions of the smaller galaxies around them. Alongside these two giants are the satellite galaxies. We have already mentioned the Magellanic Clouds orbiting the Milky Way, but there are many others. The Sagittarius Dwarf Galaxy, the Ursa Major Dwarf, the Draco Dwarf, among others. Each contains only millions or tens of millions of stars, yet each is an essential part of our surroundings. Andromeda also has its own satellites, including M32 and M110, dwarf galaxies that accompany it through space. These dwarfs are intriguing for several reasons. Many are among the oldest structures in the universe. Some formed shortly after the Big Bang and have remained relatively unchanged. Studying them is like peering into the earliest chapters of cosmic history. They are also gradually being torn apart. The gravity of the Milky Way and Andromeda strips stars from them and incorporates those stars into larger structures. This process, known as galactic cannibalism, is a natural step in galactic evolution. Yet the most compelling story in the local group is the relationship between the Milky Way and Andromeda. These galaxies are not simply coexisting, they are destined to collide. This is not speculation, but observation. Through precise measurements of Andromeda's motion, astronomers have determined that it is approaching us at about 110 kilometers per second. Some years ago, using the Hubble Space Telescope, researchers measured not only Andromeda's radial velocity, how quickly it moves toward us, but also its sideways drift across the sky. With both components, they calculated its future trajectory. The conclusion was unmistakable. The Milky Way and Andromeda will collide in roughly 4 billion years. A galactic collision does not resemble billiard balls smashing together. The space between stars is so vast that direct stellar collisions are extremely unlikely. Instead, the galaxies interpenetrate. Their gravitational fields interact violently, and both galaxies are reshaped. In the early stages, as they draw near, we will experience gravitational tides. Andromeda will swell across the night sky, appearing many times larger than the full moon, a breathtaking sight for anyone alive to witness it. Tidal forces will stretch both galaxies, pulling long streams of stars into space. As they approach further, the galaxies will pass each other multiple times. On the first pass, they will graze one another, exchanging material. Then they will drift apart before reversing course, drawn back by mutual gravity. After several encounters, they will fuse entirely. Their central regions, each hosting a supermassive black hole, will eventually merge, producing gravitational waves powerful enough to ripple the fabric of space-time. The entire process spans several billion years, a slow cosmic dance rather than a sudden blow. The final product will be a new galaxy, very unlike the original pair. Most astronomers predict an elliptical galaxy. No spiral arms, but a vast glowing sphere of stars, larger than either progenitor. This new system already has proposed names: Lactomeda or Milkdromeda, blending Milky Way and Andromeda. It will become the shared home of the stars currently belonging to both galaxies, including our Sun, if it still exists. What happens to our solar system during the collision? Likely very little in direct terms. As noted, stars rarely collide. The Sun and Earth will probably remain intact. However, gravitational disturbances may alter the Sun's orbit. Our system may be flung into the outskirts of the new galaxy or drawn inward. The night sky will change dramatically, with new constellations formed from Andromeda's stars mixed with our own. Yet another factor looms: the Sun's lifespan. 4 billion years from now, right around the time of the collision, the Sun will be nearing its old age. In roughly 5 billion years, it will expand into a red giant, potentially engulfing Earth. So humanity, if it still exists, will have needed to find a new home long before any galactic merger becomes relevant. Setting aside Earth's fate, the fusion of the Milky Way and Andromeda reminds us that galaxies are not static. They evolve, interact, merge. The universe is dynamic, constantly shifting, though over timescales far beyond human experience. Galactic collisions are common. Astronomers have observed many galaxies in various merging stages. Some are just beginning to interact, their arms twisted into strange shapes. Others are deep in the process, showing chaotic structures and intense regions of star formation triggered by the encounter. Still others have completed the merger, resulting in giant elliptical galaxies. These mergers play a central role in cosmic evolution. Small galaxies combine to form larger ones, and large ones devour smaller ones. In dense regions of the universe, galaxies tend to gather and merge over time, forming larger and larger structures. It is a kind of cosmic hierarchy in which small components build ever greater systems. The local group is not passive. It is a dynamic system in which galaxies influence each other and gradually converge. And the local group itself belongs to something even larger. It is being pulled toward the Virgo cluster, a massive assembly of galaxies about 50 million light-years away. The Virgo cluster contains more than 1,000 galaxies, many of them huge. At its center lies Messier 87, a giant elliptical galaxy, one of the largest in the nearby universe. The local group is slowly falling toward Virgo, drawn by its immense gravity. The journey will take tens of billions of years, but it illustrates that even our galactic neighborhood participates in broader cosmic flows. Beyond the Virgo cluster lie even greater structures, superclusters, filaments, cosmic voids. On the largest scales, the universe resembles a web or foam. Filaments, long chains of galaxies and clusters, connect dense regions across staggering distances. Voids are vast, nearly empty expanses with very few galaxies. All of it stretches across billions of light years. Before moving into those even larger scales, linger for a moment within the local group. There is something beautiful in the idea that our galaxy is not solitary. It has companions, neighbors, satellites. It exists within a community. Even though the distances are immense and the timescales beyond intuitive comprehension, there is quiet comfort in belonging to something larger. Just as a person belongs to a family to a community, and a community to a nation, so we belong to a solar system, the solar system to a stellar neighborhood, the neighborhood to a galaxy, and the galaxy to a group of galaxies. Each level adds context, significance, connection. The local group is our immediate cosmic neighborhood. It is the environment in which our most significant gravitational interactions unfold. It is the stage on which the Milky Way has evolved for billions of years, and it is the setting where our distant galactic future will unfold. Part 5. Superclusters and the Cosmic Web. The local group, with all its galaxies and its vastness, is only a tiny fragment of something far larger. When we widen our perspective, like pulling a camera back to reveal a broader landscape, we discover that the universe forms a striking hierarchical structure. Galaxy groups like ours gather into clusters, and clusters themselves assemble into superclusters. It is a ladder of structures, each one larger and more intricate than the last. We've already mentioned the Virgo cluster, a congregation of more than 1,000 galaxies located about 50 million light-years from us. Compared with the local group, the Virgo cluster is enormous. It contains giant galaxies, some with trillions of stars. Its gravity dominates this region of the universe, pulling not only individual galaxies toward it, but entire galaxy groups, including our own. At the center of this region lies the Virgo supercluster. This immense structure spans roughly 110 million light-years and contains at least 100 galaxy groups and clusters. The local group is just one small community on its outskirts, like living in a quiet town at the edge of a vast metropolis. For decades, astronomers believed the Virgo supercluster was the largest structure to which we belonged. But in 2014, a team of researchers made a remarkable discovery. Using galaxy motion data and three-dimensional maps of the nearby universe, they realized that the Virgo supercluster was actually only a part of a far greater structure. They named it appropriately, Laniakea. Laniakea is a Hawaiian word meaning immeasurable heaven or boundless celestial horizons. It is a beautiful name for a truly colossal structure. Laniakea stretches across roughly 520 million light-years. It contains the mass of about 100,000 trillion suns. Within Laniakea reside more than 100,000 galaxies, all linked by the same gravitational network. To visualize Laniakea, imagine a river of galaxies flowing through space. These galaxies are not scattered randomly. They follow gravitational pathways. These cosmic currents drift toward regions of higher density, toward the gravitational basins of the supercluster. It is like watching water run across a large watershed, following valleys and converging into lakes or seas. One of these gravitational hubs is the Great Attractor. Located near the center of Laniakea, about 200 million light-years from us, it is an enormous region of mass drawing thousands of galaxies toward it, including the Milky Way. Our galaxy, along with the entire local group, is moving in the direction of the Great Attractor at roughly 600 kilometers per second. We cannot see the Great Attractor directly. It lies hidden behind the plane of the Milky Way, in a region called the Zone of Avoidance, where dust and gas in our own galaxy block the light of more distant objects. But we infer its presence through its gravitational effects on the galaxies around it. It is similar to detecting a black hole. We do not see it directly, but we see how everything near it behaves. Laniakea is not the end of the hierarchy. Beyond our supercluster lie others, the Perseus-Pisces supercluster, the Hydra-Centaurus supercluster, the Pavo-Indus supercluster, and many more. Each contains tens of thousands of galaxies, each a massive structure in its own right. Together they form what is known as the large-scale structure of the universe. This vast architecture resembles a web or a sponge. Long, slender filaments hold strings of galaxies, connecting dense nodes where superclusters meet. Between these filaments lie immense voids, regions of space where almost no galaxies exist. These cosmic voids can span hundreds of millions of light-years, dark deserts nearly empty of visible matter. Why does the universe take this shape? The answer lies in its evolution since the Big Bang. In the earliest moments after the Big Bang, the universe was extremely uniform, but not perfectly so. Tiny density fluctuations existed, slightly denser regions mixed with slightly emptier ones. Over time, the denser regions drew more matter toward them, while the emptier regions lost matter. Across billions of years, these tiny early variations grew into the filaments and voids we see today. Dark matter played a crucial role. Dark matter does not emit light or interact electromagnetically, making it invisible. But its gravitational influence is unmistakable. It accounts for roughly 85% of all matter in the universe. Its gravity acted as a cosmic scaffold, pulling ordinary matter, stars, gas, galaxies, into regions where dark matter was densest. Thus formed the filaments and superclusters. When astronomers map galaxy distribution, they are essentially mapping the underlying dark matter structure. Galaxies act like tiny lights, tracing an invisible framework. It is astonishing to realize that the majority of the universe's structure is made of something we cannot see directly, only deduce. Superclusters and cosmic filaments extend across the entire observable universe. No matter where we look, we find the same pattern: galaxies clustered in filaments, superclusters at the junctions where filaments meet, and vast voids between them. This repeating architecture, echoed across immense scales, resembles a kind of cosmic fractal. Here we reach a humbling realization. The Milky Way, once seemingly immense, is only a tiny point in Laniakea. And Laniakea itself, in all its immensity, is just one of many superclusters in the observable universe. It is like discovering that your town is part of a province, that the province is part of a country, the country of a continent, the continent of a planet, the planet of a solar system, the solar system of a galaxy, the galaxy of a group, the group of a cluster, and the cluster of a supercluster. Each level adds another layer of humility. But it adds wonder, too. Each structural level reveals that the universe is more intricate, more interconnected, and more beautiful than we imagined. We are not merely inhabitants of a single planet, we are part of a cosmic network extending across billions of light years. We are gravitationally linked to galaxies we will never see, so distant that their light has not yet reached us. Visualizing these structures demands imagination. Astronomers create computer simulations showing the universe's evolution from the Big Bang to the present. In these visualizations, you can watch tiny early ripples grow over time, forming filaments, condensing into galaxies at the nodes, and assembling into the cosmic web. It is like witnessing an organism grow from seed to a vast branching tree. And here we are, on a spiral arm of the Milky Way, on the outskirts of the local group, at the edge of the Virgo supercluster, within the immense realm of Laniakea. We are part of this colossal structure, yet also able to observe it, map it, and understand it. That capacity for understanding is extraordinary. Laniakea is our supercluster, the largest gravitational structure to which we belong. Beyond its boundaries, galaxies are no longer gravitationally tied to us. They are swept outward by cosmic expansion, drifting farther and faster. In that sense, Laniakea is our broadest cosmic home. But even Laniakea, spanning 520 million light-years, occupies only a tiny fraction of the observable universe. And the observable universe itself may be just a fragment of the total cosmos. The scale expands endlessly, and our understanding must stretch with it. Reflecting on these structures can create a sense of vertigo. It is easy to feel lost, insignificant, overwhelmed by the magnitude. Yet it can also bring calm, because in all this vastness, here we are, aware, thinking, imagining horizons we will never reach physically. That awareness is a small miracle in an immense universe. Part 6. The Observable Universe and Its Limits. Up to this point, we have wandered outward through layers of structure, from our solar system to the Milky Way, from the local group to the vast realm of Laniakea. Now we reach a natural pause in that journey and face a deeper, more fundamental question. How far can we actually see? Where does our observational reach end? At what boundary does our view of the cosmos dissolve into unknowable darkness? The answer is tied directly to two key facts: the finite speed of light and the finite age of the universe. Light races through space at about 300,000 kilometers per second. It is the fastest possible speed in the universe. Nothing with mass can outrun it, and no information can travel more quickly. Yet even at that almost unimaginable pace, light needs time, enormous stretches of time, to cross the great gulfs between galaxies. The universe is about 13.8 billion years old. This means that the most ancient light we can observe has been in flight for 13.8 billion years before finally arriving here, to the mirrors of our telescopes or the retinas of our eyes. We cannot see anything whose light has not yet had enough time to reach us. It is as though we were standing at the center of an invisible sphere. We can look outward only as far as light has managed to travel during the age of the universe, and no farther. This boundary defines what we call the observable universe, the region of space from which light, or any other signal, has had time to arrive since the Big Bang. Everything just beyond that spherical shell is, for us, invisible and effectively disconnected. But here we encounter an intriguing complication. The observable universe does not have a radius of 13.8 billion light-years, as a first guess might suggest. Instead, its radius is about 46 billion light-years. How can that be? The explanation lies in the expansion of the universe itself. The cosmos is not merely large, it is growing. Space is stretching like rising dough, carrying galaxies along for the ride. When the light from a distant galaxy began its journey billions of years ago, that galaxy was much closer to us than it is now. As the light traveled, the space it crossed continued to expand, pushing the galaxy farther and farther away. By the time the light finally reaches us, the galaxy that emitted it has moved to a much greater distance than when the light first set out. Because of this ongoing expansion, the present-day size of the observable universe is about 93 billion light-years across. That is the current diameter of the cosmic bubble within which lie all the objects whose light has ever had time to reach our little planet. Imagine an immense sphere with Earth at its center, extending 46 billion light-years in every direction. That shimmering boundary, which we can only define mathematically, is the edge of the observable universe. It is crucial to emphasize that the observable universe is not the whole universe. It is only the portion accessible to us. The full universe may be much, much larger than the part we can see. It might even be infinite, extending endlessly in all directions. We simply do not know, because anything beyond our cosmic horizon is forever hidden from direct observation, at least with the laws of physics as we currently understand them. The situation is like standing alone in the middle of a calm ocean at night. You can see out to the horizon, perhaps a few kilometers in every direction, but you know intuitively that the sea continues far beyond what your eyes can reach. The horizon is not the edge of the ocean, it is merely the limit of your vision. Likewise, the edge of the observable universe is not the border of all reality, only the limit of what light has had time to show us. This horizon is not a rigid shell, it is a moving frontier. With every passing second, more light from ever more distant regions has time to arrive, and the observable universe, as such, grows. At the same time, however, because the expansion of the universe is accelerating, some galaxies are receding from us so quickly that light emitted now will never catch up to us. They are carried away by the swelling fabric of space, faster than light can bridge the gap. Those galaxies eventually cross beyond our horizon and slip from view forever, like ships sailing over an ocean horizon that can never return. How many galaxies lie within this observable bubble? This question has fascinated astronomers for decades. To approach an answer, they carried out one of the boldest and most patient observational experiments in the history of astronomy: the Hubble Deep Field. In 1995, astronomers pointed the Hubble Space Telescope at a tiny patch of sky that appeared completely empty. No bright stars, no nebulae, no known galaxies, just a dark scrap of sky, smaller than the head of a pin held at arm's length. To any casual observer, it would have looked like a pointless target. Yet for 10 consecutive days, Hubble took long exposures of this region, patiently gathering the faintest trickles of light. When the images were finally processed, the result was breathtaking. In that minuscule, seemingly empty patch, Hubble revealed roughly 3,000 galaxies. Some were relatively nearby spirals, grand, luminous pinwheels of stars. Others were more distant ellipticals, smooth ovals of light. Many were incredibly remote galaxies, whose light had been traveling for billions of years before reaching us. We were seeing them as they were when the universe was still young, only a few billion years after the Big Bang, frozen in cosmic childhood. Astronomers repeated the experiment with even deeper exposures. The Hubble Ultra Deep Field uncovered around 10,000 galaxies in a similar region of sky, pushing our view still farther back in time. Later, the Hubble Extreme Deep Field combining many days of observations, revealed galaxies even more distant, some of the farthest and faintest ever seen, tiny red smudges at the very edge of visibility. By extrapolating these results to the entire sky, astronomers can estimate how many galaxies populate the observable universe. The numbers suggest there are at least 200 billion galaxies, and probably more. Some recent studies even propose that there could be on the order of 2 trillion galaxies. It is a figure that defies everyday intuition, a number so large that our minds quickly lose grip on it. Each of those galaxies holds, on average, hundreds of billions of stars. Multiply 200 billion galaxies by hundreds of billions of stars each, and you obtain a number around 10 to the 24th power, a 1 followed by 24 zeros. That is roughly how many stars fill the observable universe. It exceeds the number of grains of sand on all the beaches of Earth. It surpasses the number of seconds that have elapsed since the Big Bang. It is, quite literally, astronomical in every sense of the word. And each of those stars may host planets. In the era of exoplanet research, we have learned that most stars likely possess at least one planet, and many have entire families of worlds. The number of planets in the observable universe is therefore even greater, perhaps hundreds of thousands of billions, a cosmic archipelago of unimaginable richness. How many of those worlds harbor life? We do not know. We lack the data to make a reliable estimate, and for now, everything remains speculation. But even if only a tiny fraction of those planets support life, the absolute number of inhabited worlds would still be enormous. And if only a fraction of those living worlds give rise to intelligent beings, we would still be talking about millions, or perhaps billions of potential civilizations scattered across the cosmic sea. Here we encounter one of modern astronomy's great puzzles. The universe is so vast, with so many stars and planets, that it seems statistically unlikely we are alone. Yet we have found no clear evidence of other intelligent life. We have not detected unambiguous radio signals from alien civilizations. We have not seen unmistakable megastructures built by advanced species. We have not found probes lurking in our solar system or artifacts drifting through interstellar space. On the surface, the universe appears silent, despite its immense abundance. This contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked during a casual conversation at lunch, "Where is everybody?" Many explanations have been proposed. Perhaps intelligent life is extraordinarily rare, and we are a statistical miracle. Perhaps civilizations tend to destroy themselves before achieving long-term interstellar communication, victims of their own technology or environmental collapse. Perhaps the distances are simply too immense, and civilizations do exist but remain forever isolated, like islands separated by an uncrossable ocean. Or perhaps we have been looking in the wrong ways, or for the wrong kinds of signals, blind to forms of communication we do not yet understand. Whatever the answer, the sheer scale of the observable universe confronts us with profound questions about our place within it. We are one possible civilization on one out of an unthinkable number of planets, circling one ordinary star in one galaxy among billions. The scale is so immense that our minds strain to grasp it, and yet we keep trying, again and again, to push our understanding a little farther. And yet, here we are, contemplating all of this. We are capable of peering back in time to the universe's early ages, of counting galaxies and estimating the number of stars and planets, of asking where we fit into this enormity. That capacity for reflection and understanding is itself extraordinary, a quiet light of consciousness shining against the dark backdrop of space. The observable universe is our stage, the region of the cosmos we can study, explore, and attempt to comprehend with telescopes, equations, and imagination. Beyond it, the universe continues, but lies beyond our reach. It is as though we live on an island in an endless ocean. We can come to know every beach, every hill, every forest of the island, but the waters beyond remain mysterious, their shores forever hidden below the horizon. And that invisible boundary, that cosmic horizon, naturally draws our thoughts outward to a final set of questions. What lies beyond? Is the universe infinite, stretching on without end? Does it curve back on itself in some higher dimensional way? Does it have an edge? And if so, what, if anything, lies outside it? Those questions carry us beyond observation and into the realms of theory and speculation, into the next chapter of our journey, where we explore what may exist beyond the limits of what we can see. Part 7. Beyond the observable, infinity and the multiverse. We have reached the boundary of everything we can directly observe. The observable universe, immense as it is, with its 93 billion light-years of diameter and its trillions of galaxies, is the full extent of what our instruments can measure. But an inevitable question rises from that edge. What lies beyond? Does the universe end at that horizon, or does it continue outward into realms we cannot access? Most cosmologists agree that the universe does not end at the border of the observable. Instead, it stretches far beyond, perhaps endlessly. The cosmic horizon is not a physical wall. It is merely the limit of our vision. Like standing on a ship surrounded by open sea, we see only as far as the horizon, even though we know the ocean continues. The horizon moves with us, always at a fixed distance, yet we never reach the ocean's final edge. If the universe continues beyond what we can observe, how much larger is it? Now we enter speculative yet profoundly intriguing territory. Several possibilities unfold. One possibility is that the universe is infinite, no edges, no boundaries, extending forever in every direction. If this is the case, then beyond our observable sphere, there would be more galaxies, more clusters, more cosmic architecture without end. This scenario aligns with current observations. Measurements of the universe's geometry using the cosmic microwave background suggest that space is extremely close to flat. A flat universe can extend infinitely. If the universe is infinite, then everything allowed by physical law must occur somewhere. There must be infinite galaxies, infinite stars, infinite planets. And in an infinite cosmos with infinite combinations of circumstances, even the most improbable events must happen. There would be other Earths, other stars identical to our Sun, other versions of you living slightly different lives. Strange as it sounds, these are straightforward consequences of an infinite expanse. We will never be able to verify if the universe is truly infinite. We can only see as far as our finite horizon allows. But based on its apparent flatness and uniformity, an infinite universe remains a compelling hypothesis. A second possibility is that the universe is finite but unbounded. This seems contradictory, but it is entirely plausible if space has a curved geometry. Imagine the surface of a sphere. If you walk in a straight line across Earth, eventually you return to where you began. The surface is finite. It has a measurable area, but it has no borders or edges. There is no cliff from which you can fall. Similarly, the universe could have a geometry such that, if you traveled far enough in a straight line, you would eventually circle back to your starting point. The cosmos would have a finite volume, yet no physical boundary. This idea is consistent with certain interpretations of cosmic curvature, though current evidence leans slightly toward flatness and infinity. Beyond these possibilities lies an even more radical idea proposed by many physicists: the multiverse. According to this concept, our universe is not the whole of reality. Other universes exist beyond our own, completely detached from it, each with its own physical laws, constants, and evolutionary history. Several versions of the multiverse concept exist, each grounded in different theoretical frameworks. One arises from cosmic inflation, the theory describing the universe's rapid early expansion. Inflation may not have ended uniformly everywhere. In some regions it stopped, producing universes like ours. In others, it continued, spawning new universes. This eternal inflation would create an infinite collection of bubble universes, each isolated, each unique. Another version comes from string theory, which attempts to unify all fundamental forces. String theory predicts extra spatial dimensions, and the way those dimensions fold or compactify could vary across different regions, producing universes with different physical constants. This yields a vast landscape of possible universes, each realized somewhere within the multiverse. A third version comes from the many worlds interpretation of quantum mechanics. According to this view, every quantum event branches reality into multiple outcomes. Flip a coin. In one branch, the result is heads, in another, tails. Both branches exist simultaneously, but they never interact. If true, the number of parallel universes is unimaginably large, increasing constantly as reality branches at every instant. These ideas are speculative. We have no direct evidence for the existence of other universes, and may never have any. By definition, they lie beyond our cosmic horizon. We cannot see them, cannot travel to them, cannot communicate with them. Yet physicists explore these theories because they offer solutions to puzzles within our own universe. One such puzzle is the fine-tuning problem. The constants of physics, gravity's strength, the cosmological constant, the masses of fundamental particles, seem exquisitely tuned to allow the existence of stars, planets, and life. A tiny deviation in any of these values would make the universe sterile. Is this coincidence? Intentional design? Or, as the multiverse suggests, are we simply inhabiting one of the rare universes where conditions happen to allow observers to exist? We cannot exist in universes where the constants forbid complexity. So naturally, we find ourselves in one that permits it. This is the anthropic principle. The multiverse also raises profound philosophical questions. If infinite universes exist, does that make ours less special? Or does it remain unique simply because it is the one we can experience? If countless versions of you exist, which one is you? Does that question even make sense? These ideas can feel overwhelming or unsettling. The notion that our universe, already vast beyond comprehension, might be only one bubble in an immeasurable ocean of universes challenges intuition. Yet it is also liberating. It reminds us that reality may be far deeper, stranger, and richer than any current theory captures. Crucially, these concepts are not arbitrary fantasies. They emerged naturally from our best mathematical models of physics, from inflation theory, quantum mechanics, and attempts at unification. Whether the multiverse exists or not, the fact that such ideas arise from rigorous reasoning highlights the remarkable power of the human mind. Beyond the observable universe lies mystery. Perhaps more of the same, more galaxies, more filaments, extending without end. Perhaps entirely different universes, governed by unfamiliar laws. Perhaps realities we have not yet imagined. Whatever the truth, one fact remains. The universe is vastly larger than the tiny region we can observe. Our horizon is not an end. It is merely the beginning of the unknown. And on that frontier, between what we can see and what we can only theorize, we encounter some of the most profound questions humans have ever asked. These questions may never have final answers, yet the very act of asking them, of probing the boundaries of possibility, of reaching with imagination beyond the limits of observation, is an essential part of being human. We explore not only the physical universe, but the conceptual one. And in that sense, the universe beyond the observable is a real landscape for us, even if we never touch it. So when you gaze at the night sky and see the stars scattered across the darkness, remember that what you witness is merely the beginning. Beyond those stars lie billions of galaxies. Beyond those galaxies lie structures of staggering scale. Beyond the observable universe may lie infinity. And beyond even that, who knows? The mystery remains, calling us to keep wondering, keep exploring, keep imagining. Part 8. The story of how we discovered all this. Everything we have explored, from the structure of the Milky Way to the possibility of a multiverse, was not always part of human knowledge. There was a time when humanity believed Earth stood at the center of creation, that the sun and stars circled around us, and that the universe was small and unchanging. The journey from that narrow worldview to our current understanding is a story of curiosity, ingenuity, and perseverance across centuries. We begin with Galileo Galilei. In 1609, Galileo aimed a simple telescope at the night sky. He did not invent the telescope, but he was among the first to use it systematically for astronomy. What he saw transformed everything. He observed mountains and craters on the moon, proving it was not a perfect sphere. He discovered 4 moons orbiting Jupiter, showing that not everything revolved around Earth. He recorded the phases of Venus, evidence that Venus orbited the Sun. And when he directed his telescope at the Milky Way, he resolved its glow into thousands of individual stars. These revelations were revolutionary. They challenged the geocentric worldview that had dominated for centuries. Galileo provided observational support for Copernicus's heliocentric model, where Earth and the other planets orbit the Sun. For this, he faced fierce opposition from the Catholic Church, was tried for heresy, and spent his final years under house arrest. Yet his observations could not be erased. The telescope had revealed a new truth. After Galileo, astronomy advanced rapidly. Isaac Newton developed the law of universal gravitation, explaining how planets trace predictable paths. In the late 18th century, William Herschel built ever larger telescopes and discovered Uranus, the first planet unknown to the ancients. Herschel also attempted to map the Milky Way by counting stars in all directions, correctly concluding that it was shaped like a disk. In the 19th century, astronomers began measuring stellar distances using parallax, the apparent shift of a star's position when seen from opposite sides of Earth's orbit. In 1838, Friedrich Bessel measured the distance to 61 Cygni, confirming that stars were staggeringly far away. This enlarged our sense of cosmic scale dramatically. Then came spectroscopy, the splitting of light into its component colors. Astronomers learned they could identify the chemical makeup of stars by studying their spectra. They also discovered the Doppler effect in light. When an object recedes, its light shifts toward red. When it approaches, toward blue. This tool would prove essential for the next great leap. We've already mentioned Edwin Hubble and his historic discovery in 1920 that spiral nebulae were entire galaxies beyond the Milky Way. But Hubble's work continued. He measured distances and velocities for many galaxies. In 1929, he published his most famous finding: galaxies are receding from us, and the farther a galaxy is, the faster it recedes. The universe is expanding. This discovery had profound implications. If the universe is expanding now, then in the past it must have been smaller. Rewind far enough, and everything must have been compressed into a single, incredibly dense point. This insight led to the Big Bang theory, first articulated by the Belgian priest and physicist Georges Lemaitre. Not everyone accepted the Big Bang immediately. Some astronomers favored the steady-state model, which suggested the universe had always existed in roughly the same form. But in 1964, two radio engineers, Arno Penzias and Robert Wilson, accidentally discovered the cosmic microwave background, faint radiation arriving uniformly from all directions, the cooling echo of the Big Bang. This evidence confirmed the Big Bang model and earned both men the Nobel Prize. With the Big Bang established, cosmologists could begin constructing a coherent history of the universe, how the first atoms formed minutes after the Big Bang, how the first stars ignited hundreds of millions of years later, how those stars assembled into galaxies, and how galaxies evolved over billions of years. To test these ideas, astronomers needed clearer observations. Earth's atmosphere blurs starlight, limiting ground-based telescopes. The solution was to place telescopes in space. In 1990, NASA launched the Hubble Space Telescope. Hubble became one of the most productive scientific instruments ever built. For more than 30 years, it captured breathtaking images of nebulae, galaxies, star clusters, and distant cosmic structures. It produced the Hubble Deep Field, revealing thousands of galaxies in a tiny patch of sky once thought empty. It measured the universe's expansion rate. It helped discover that expansion is accelerating, driven by dark energy. It studied exoplanet atmospheres. It imaged galaxies in collision. It revealed supermassive black holes at galactic centers. Hubble's images were not only scientifically valuable, they were beautiful. They inspired millions, making the cosmos accessible to the public. They appeared in classrooms, documentaries, books, exhibitions. Hubble transformed our cultural relationship with the universe. But science marches on. In December 2021, NASA launched Hubble's successor, the James Webb Space Telescope. With a primary mirror measuring 6.5 meters, far larger than Hubble's, Webb is designed to observe primarily in infrared, allowing it to see through cosmic dust and study the earliest galaxies ever formed. Webb's first images, released in July 2022, were astonishing. They showed galaxy clusters in unprecedented detail. They revealed exoplanet atmospheres. They captured star-forming regions with striking clarity. And they began detecting some of the oldest known galaxies, objects shining only a few 100 million years after the Big Bang. Webb is built to answer some of astronomy's most fundamental questions. How did the first galaxies form? How do galaxies evolve? How are stars and planets born? Are there signs of life in exoplanet atmospheres? In the coming years, Webb will undoubtedly reshape our understanding of the universe and raise new questions we cannot yet imagine. Meanwhile, ground-based observatories grow more powerful. Chile's Very Large Telescope, the Keck Observatory in Hawaii, and the upcoming Extremely Large Telescope, now under construction, use adaptive optics to counteract atmospheric distortion, producing images nearly as sharp as those from space. Radio astronomy, too, revealed a new universe. The Arecibo telescope in Puerto Rico, sadly collapsed in 2020, was for decades a titan of discovery. The Event Horizon Telescope, a global network of radio dishes, captured the first direct image of a black hole in 2019, a landmark achievement. And astronomy entered a new era with gravitational waves, ripples in space-time produced by catastrophic events like merging black holes. The LIGO and Virgo detectors have opened a new channel of cosmic observation, allowing us to listen to the universe. The story of how we learned all this is a story of human collaboration across centuries. each generation built on the work of the last. Galileo pointed a simple telescope at the sky. Newton built the mathematical framework of gravity. Hubble measured the expansion of space. Penzias and Wilson detected the Big Bang's afterglow. And now, with instruments like Webb, we continue the journey. This history teaches us something important. Knowledge is cumulative. No discovery exists in isolation. Each advance relies on earlier insights, earlier tools, earlier questions, and each answer leads to new mysteries, pushing exploration forward. It also shows that curiosity is the engine of progress. Astronomers spent their lives gazing upward, not for practical gain, but because they wanted to understand. They wanted to know what those lights in the sky were, how far they lay, how they worked. That pure desire to know has led to some of humanity's greatest discoveries. Part 9. The Philosophy of Cosmic Smallness and Our Place in the Universe. We have come a long way, from the Milky Way to the observable universe, from our stellar neighborhood to Laniakea, from Galileo's first observations to the images of James Webb. Now it is time to pause and reflect on what all this means. What is our place in this immensity? What does this story tell us about ourselves? In 1990, the Voyager 1 spacecraft, after completing its primary mission in the outer solar system, turned back toward home. At Carl Sagan's suggestion, NASA instructed Voyager to take one last photograph of Earth from a distance of about 6 billion kilometers. In that frame, our world appears as a tiny spark, hardly more than a pixel, hanging inside a band of scattered sunlight. Sagan named the image the pale blue dot, and wrote a famous meditation about it. In essence, he reminded us that on that single point live everyone we love and everyone we have ever heard of, that every king and peasant, every soldier and artist, every saint and every criminal, every victory and every tragedy in human history has unfolded on that minuscule mote of dust suspended in a sunbeam. Those words capture something essential about our condition. Seen from far away, everything we treat as overwhelmingly important, our ambitions, our fears, our conflicts, our triumphs, takes place on an almost unbelievably small stage. Earth, our home, is just a point in the great darkness, and yet it is the only home we have, the only place where we know the universe has learned to think and feel. This perspective can trigger two opposite reactions. On the one hand, it can make us feel insignificant. If we are so tiny, if our planet is only a grain of dust in the cosmos, does anything we do really matter? Do our lives, our struggles, our dreams have any meaning at all? On the other hand, the same view can have the reverse effect. It can make this pale blue point feel infinitely precious. It can remind us that we must take care of it, because it is all we have. It can heighten our awareness of how fragile we are and how deeply we depend on one another as passengers sharing a very small refuge in an enormous void. There is something more. In spite of our physical smallness, we are capable of understanding all this. We can measure galaxies billions of light years away. We can estimate the age of the universe. We can even imagine multiverses beyond it. We are small in size, but not in awareness. Our minds can embrace scales our bodies will never reach, turning equations and images into a mental map that runs from atoms to galaxy clusters. Centuries ago, the philosopher Blaise Pascal described this paradox. He wrote that a person is weaker than a reed, easily crushed, yet more noble than what kills them, because a human being knows that they die, while the universe knows nothing at all. We are fragile, but we understand our fragility, and that knowledge changes everything. That is our peculiarity. We are matter that has become conscious of itself. We are the universe looking back at the universe. In us, the cosmos has developed the ability to ask questions about its own origin and destiny, to marvel at itself, to feel awe. When we compare the size of the Milky Way with the observable universe, the difference is immense. The Milky Way, 100,000 light-years across, is only one among billions of galaxies. It is like a single coin lying on the floor of an entire continent, a drop in a shoreless sea. And Earth, tucked inside that galaxy, is smaller still, a tiny speck of dust on that coin, circling an ordinary star in an ordinary arm of an ordinary spiral. Yet this smallness does not diminish us. It grants perspective. It reminds us that our everyday problems, however urgent they feel, are brief and limited in scale. An argument, a financial worry, a personal disappointment, each of these dramas takes place on that same pale blue dot. Viewed from the outside, on cosmic scales, they are fleeting echoes that quickly fade. This does not mean our problems are unimportant. For us, they matter profoundly, and they shape our inner worlds. But the cosmic perspective can help us place them in context. It can keep us from losing sight of what truly has lasting value: relationships, experience, curiosity, love, beauty. Sometimes, simply recalling the image of that distant Earth can be enough to soften a hard day. The thought that our worries occupy a tiny corner of a tiny world can create just enough distance to let us breathe, to step back from the noise, to choose kindness over anger and curiosity over fear. The same perspective also underscores our responsibility. As far as we currently know, Earth is the only place in the universe where life definitely exists. Life almost certainly thrives elsewhere, but we have not found it yet. For now, we are the caretakers of this pale blue dot. We are responsible for safeguarding life here, preserving biodiversity, and keeping our planet habitable for those who will come after us, whose names we will never know. Sagan ended his reflection on the pale blue dot by pointing out that this distant view exposes the absurdity of human arrogance. For him, the image emphasized our duty to treat one another more kindly and to protect that tiny blue world, the only home our species has ever known. From so far away, borders vanish, flags disappear, and only a single point remains, fragile and solitary. The comparison between our galaxy and the universe teaches humility. It shows us we are not the center of anything, but it also teaches wonder. It shows that we belong to something far larger, a cosmic story that began nearly 14 billion years ago and will continue for eons after we are gone. Within that story, we hold a unique role. So far as we are aware, we are the only beings in this region of space able to understand the universe at all. We are the eyes and ears of the cosmos, the means by which the universe becomes aware of itself. Through our science, our art, and our questions, the cosmos gives itself a voice. That capacity to understand carries a sense of quiet amazement. When you look up at the night sky and recall what you know, the distances, the scales, the galaxies hidden beyond the stars you can see, it is natural to feel a tangle of emotions: wonder at the vastness, humility before our smallness, gratitude for the chance to be here and witness any of it, perhaps even a kind of calm. There is something deeply soothing in the sheer size of the cosmos. Our daily worries, while real and pressing, are tiny against that backdrop. The universe existed for billions of years before we were born, and will continue for billions more after we are gone. Seen in that light, it becomes easier to loosen our grip on certain anxieties, to accept that not everything is under our control. This brings us to the end of our journey through cosmic scales. We have traveled from the Milky Way to the observable universe and beyond. We have explored our stellar neighborhood, visited other galaxies, met the local group and Laniakea. We have stared toward the cosmic horizon and wondered what lies past it. We have traced the history of our discoveries, from Galileo to James Webb. And finally, we have reflected on what all this means for us. The answer to our original question, how big is the universe compared with our galaxy, is now clear. The Milky Way is immense, a disk 100,000 light-years wide with hundreds of billions of stars. Yet compared with the observable universe, it is only a spark, one galaxy among billions. It is an apple tree in an endless orchard, a single drop in a bottomless ocean. Even when you are lying in a dark room with the curtains drawn, that immensity does not vanish. The same universe of galaxies and clusters is still there outside the walls, and every photon that reaches your eyes has traveled a long path to bring you a fragment of that greater story. The astonishing thing is that from within that drop, from within that spark, we can contemplate the whole ocean. We can imagine the totality. We can ask where we belong inside it. And in that immense setting, we can find not horror or despair, but wonder and a deep, quiet serenity. In the end, we do not need to be large to matter. We do not need a central seat in the cosmos to have value. Our worth comes from our capacity to experience, to care, to question, to be astonished. That value is not measured in light years, but in the depth of our inner life. In that realization, there is peace. Knowing that our struggles and anxieties are small against the universe can be comforting, not to dismiss them, but to give them proportion. We ride a silent spiral of stars in a remote corner of a vast universe. That simple fact reminds us that life is brief, fragile, and precious. So we reach the close of this journey, from the Milky Way to the observable universe and beyond, from the nearby to the inconceivably distant, from science into philosophy, all bound together by a single thread, the human urge to know and to marvel. Good night. May you rest under a sky that holds more mysteries than we will ever be able to count, and may the calm of that immensity follow you into your dreams. If you enjoyed this voyage, feel free to leave a like and subscribe so we can keep exploring together. Very soon we will talk about other galaxies, about black holes, and about the ultimate fate of the cosmos. Topics that, like this one, remind us that there is always more waiting to be discovered. Sleep peacefully, because even though we are small, we live in a universe that grants us the wonder of contemplating it.